Hello all. Today's lecture is about magnetic circuits. First, we will see the outlines of the lecture. We will see magnetic field, magnetic materials and their properties, I-H relationship and B-H relationship, then the magnetic and electric circuits and similarity between electric and magnetic circuits, the laws impose magnetic and electric circuits, Faraday's law of induction, then self-inductance of a coil. After that, mutual inductance between two coils, two types of magnetic losses, which are the eddy current loss and the hysteresis loss. Last but not least, the hysteresis loop for alternating current AC feeding magnetic circuits. Magnetic circuit. What is a magnetic field? The magnetic field is a space around poles of magnet. The field around a bar magnet represented by lines of force. These lines of force originate from the north pole and terminates at the south pole. The flux lines, which are shown here, show the direction and intensity of this field at all points around the magnet. The lines are denser at each pole, the north and south pole, and as we go away from the poles, the number of flux lines decreases. Magnetism is the force of attraction or repulsion that acts between magnets and other magnetic materials. If we have like poles, north pole and north pole, then they repel. And if we have different poles, north and south, they attract. Then unlike poles attract and like poles repel. For the magnetic field, we have the magnetic field strength or intensity, or called the magnetizing force. All are the same. Magnetic field intensity or magnetizing force, H, is the magnetomotive force. This is the magnetomotive force per unit length. It is the magnetomotive force per unit length, which is equal to the magnetomotive force over the length of the magnetic path. The magnetomotive force is equal to number of turns times current, and L is the length of the magnetic path. We have flux and flux density. The flux, it is the total number of magnetic lines, which is measured in Weber. Those are the magnetic lines, and they have direction which originate from the North Pole and terminate at the South Pole. For the flux density, which is the number of lines per unit area, the total flux passing perpendicular through an area by this area, or B equals phi divided by area in Webers per meter square or Tesla. There is another measurement or unit of flux density, which is Gauss. We have 1 Tesla equals 10,000 Gauss. Then, or now, we will see the I-H relationship, which is using Ampere's law, discovered by Andrea Ampere in 1826, relates the integrated magnetic field intensity H around a closed loop to the electric current passing through the loop. We have the integration of HDL across a closed loop will get the I net through this closed loop. If we are at distance r from the wire, we have the wire, and we are at distance r away from the wire, then the integration over a closed path of HDL. The integration of dl, we have a small part dr. If we integrate over dr, we get the 2 pi r, which is the circumference of the circle, and which is equal to the I net, which is the current of the wire, equals I. For regular field strength, I equals HL, where L is the length of the closed path. H direction can be deduced according to Ampere's or right thumb rule, Ampere's right hand rule, where the thumb is pointing in the direction of the current, as shown here. We have the thumb in the direction of the current, and the other uh, fingers of the hand are pointing to the direction of H or LB. These circles or concentric circles around the wire show the direction of the magnetic field intensity B. Now we will see the BH relationship. The magnetic field intensity H produces a density, a flux density B, everywhere it exists. Everywhere H exists, it produces magnetic flux density B. These quantities are related by B equals mu times H, where mu equals mu naught, mu R. This is in the linear region, as we will see the BH curve of the different materials. Mu is a characteristic of the material of medium and is called the permeability of the medium. And we will see in the next few lines what is the permeability. Mu naught is the permeability of free space, or air, equals 4 pi times 10 power negative 7 Henry per meter. Mu r is the relative permeability of the medium, which is the permeability of the material as a percentage or times of the permeability of free space. What is permeability? Permeability is the measure of ease with which magnetic flux lines can be established in the material. It measures the easiness of producing magnetic flux lines or establishing magnetic flux lines in a material. The materials or magnetic materials and their properties, we can classify materials or the magnetic materials to diamagnetic materials, where the permeability of diamagnetic materials is slightly less than permeability of free space. Examples for diamagnetic materials is silver, water, and copper. Those are diamagnetic materials and can be used for magnetic shielding. For the paramagnetic materials, the permeability of paramagnetic materials is slightly greater than free space. And for the materials that can be used as electromagnets or cores of transformers, these are the ferromagnetic material, which are made of iron. Substances like iron are called ferromagnetic or iron alloys. The magnetic force of attraction experienced by ferromagnetic material may be 5,000 times or 1,000 times that experienced by paramagnetic material, which are the materials before that. Then ferromagnetic materials can be used for electromagnets and for the cores of transformers, as we will see in the next few slides. Now we will discuss the relationship between B and H, or the BH curve. We have a toroid carrying current I. L is the length of the flux path, which is the mean length of these paths. The mean length L here. E is the cross-sectional area, and N is the number of turns. H represents the x-axis, and B represents the y-axis. Also, we can H is related to I and B is related to phi. We can have I as the x-axis and phi as the y-axis. As the value of mu, which is permeability, is large, or we have larger value of it, the larger is the flux density for given length L. Also, H is proportional to I, where HL equals Ni for a toroid having number of turns N. Ni equals HL. L over N is constant proportionality. As we increase I, H will increase. The larger the value of I, the larger the value of H. As I increases, H increases, then the flux density increases since the total flux increases for a given equation phi, or the relation between phi and b. Phi equals b times area. As we increase H, we have the first part is a linear region. Then as the material increase I, as we increase I, the rate of increase of B will be B or phi will be slower. Then we reach the saturation region where the material has saturated or reached the maximum number of flux lines that can pass through this section. If the current decreases, we will return back over the dotted line, and a part of the magnetism is stored in the material, which is the residual flux density. Here we see different magnetizing curves between the flux density B, which is the y-axis, and the magnetizing force H as the x-axis for different materials: cast iron, cast steel, and silicon sheet steel. Now we will see from Ampere's law applied to magnetic circuit, solid core. We have the integration of HDL over a closed path equals HL equals, we can replace H by B over mu times L, which is equal to Ni. L is the average or the mean magnetic path of flux. We can also obtain phi as the integration of B, the area, or B times the area. So we can replace B by phi divided by area. Then we have Ni equals phi times L over mu times area. The part L over mu times area will be represented as the R, or the magnetic path reluctance, which is analogous to the resistance of the wire. There are two types of losses in the magnetic pulses. We have fringing of flux lines, as the flux lines pass from one material to another, from the material in the upper part to the air gap. Then the flux lines were bond or fringe until they return back to the same material. Also, we have part of flux lines which is passing outside the magnetic path, or outside the magnetic material, due to saturation of the magnetic material with flux lines. Leakage flux is considered as type of losses due to flux outside magnetic material. We have less leakage flux for higher permeable material, or for materials with higher permeability. The reluctance R represents the resistivity to flux in the magnetic path, which is calculated or having the unit of ampere turn per Weber, where R equals the length of the magnetic path divided by the permeability multiplied by the cross-section area of the core. What is the difference, or why is the reluctance of figure B is larger than the reluctance of figure A? We can see that for figure B there is an air gap, and air gap has a reluctance equals length of air gap divided by mu of the air gap, which is mu naught, times the area of the air gap. The mu of the air gap, which is very small, 4 pi times 10 power negative 7, then the reluctance of the air gap will be very high, as mu is very small. Then the reluctance of figure B, due to the presence of the air gap, will be bigger than the reluctance of figure A. Now we will see the similarity between magnetic and electric circuits. For the electric circuits, we have electromotive force, which is the driving force for the current the analogy or the similar to this electromotive force is the magnetomotive force, which is the initialize or the force that produces the flux lines for the current, electric current in the electric circuits, which is the passage of electrons in a wire, is similar to the magnetic flux, which is measured in Weber phi, which is measured in Weber in the magnetic circuits. For the resistance, which is the resistance of the wires to the passage of current, measured in ohms, similar to it in magnetic circuits is the reluctance, which is the resistance of the magnetic pulse to the passage of flux. The constant in electric circuits, which is electric conductivity, which measures the conductivity of the wires or the easiness of the passage of current in wires. We have magnetic permeability mu, which represents the measure of ease of the establishment of flux lines in magnetic circuits. The next part is Faraday's law of induction, which is the base theory of induction furnaces, transformers, and many other devices. Faraday's law of induction is a basic law of electromagnetism relating to the operating principle of transformers, electric motors, generators, and induction furnaces. The law states that the induced EMF generated is proportional to the rate of change of magnetic flux. Then we must have a changing flux with time, having a rate of change d phi by dt, to have an induced EMF in the coil. Here we can see that the magnet north and south is moved to the right side to produce a flux that is changing. Then at the terminals of this coil we will see an induced EMF due to the changing flux. We have a term called flux linkage, which is equal to the number of turns times the flux, which represents the number of flux lines that link an n turns of a coil with each other. This is statically. We have E equals n d phi by dt, and we have to increase a negative sign, which is according to Lenz's law, which states that the induced EMF is producing a flux and current that opposes the flux producing it. For any magnetic material or magnetic circuit, each coil has connected to a source has its self-inductance. This is due to the electromagnetic effect of the back-induced EMF induced in the coil opposite to the applied voltage. Then it produces a self-inductance. The self-inductance is related or can be obtained by using this equation, which is dynamic equation, n d phi by di, which depends upon the rate of change of flux with respect to current. The flux and current are the flux and current of this coil, of the same coil. Then this is called self-inductance, or the inductance of the coil due to its current and the changing flux. Statically, L, the self-inductance, equals lambda over I, or the flux linkage divided by I, which is n phi divided by I. We can substitute phi by b times area equals nb times area divided by I. We can substitute b with mu times h. We have n mu times h times area over I. We can also substitute I by HL divided by N. Now we have H cancelled with H, and N is the denominator of the denominator. It will be a numerator. Then N times N equals N square divided by L over mu times the area, where L divided by mu times the area is the reluctance of the magnetic path. We have the equation of Faraday's law equal E equals n d phi by dt. We can multiply this equation by di and divide by di. Now we have E equals n d phi by di, which is the self-inductance times di by dt. Then the induced EMF equals L di by dt. This is the relation between the induced EMF, self-inductance, and the rate of change of current with time. For the self-inductance of the coil, we have the power consumed equals E times I. The induced EMF E equals L di by dt times di times I. Now we multiply both sides by dt. We have power dt equals Li di. If we integrate both sides, integration of power dt equals integration of Li di. The integration of power, we get the energy, and the integration of I di, we increase the power of I by 1 and divide by the new power. We have I square divided by 2. Then the energy stored in a coil equals half Li square in joule or watt second. We have another term which is a mutual inductance, the mutual inductance between two coils. If we have two coils, and this is the principle of transformers. If we have two coils, a coil connected to the source at this side, at the left side, the supply will pass current I. This current I will produce a flux. If we connect another coil at the other side of the core, the flux will pass in the magnetic path and link the number of turns of the second coil, which is N2. The flux is produced due to the current and flux of coil 1. Then there is a mutual inductance between these two coils, and the mutual inductance M, or the induced EMF E2 equals N2 d phi by dt, or d phi 1 by dt. If we multiply and divide by di1, and here is d phi 1, then we have induced EMF equals mutual inductance of coil 2 due to flux and current of coil 1 times di by dt, or di1 by dt. This is I1. Then the mutual inductance from coil 1 to coil 2, M21, equals number of turns of the second coil and the rate of change of flux of the coil 1 divided by with respect to the current I1. Similarly, if we put the supply or connect the supply to the other coil or the secondary or the coil at having number of turns N2 or coil 2, then a current I will pass, producing a flux phi 2. This flux will link the number of turns N1 and produce an induced EMF in it, which is called E1. Then we have a mutual inductance of coil 1 due to flux of coil 2, which is equal N2 rate of change of flux of phi 2. This is phi 2. This is phi 2, not phi 1. This is phi 2. Rate of change of phi 2 with respect to I2. The self and mutual inductances of two coupled coils can be correlated, or the relation between the mutual and self inductance M equals K root L1 times L2, where L1 L2 and self inductances of coil 1 and coil 2. Now we need to know what is K. K is the coupling coefficient or coupling factor, or coefficient of coupling or coupling factor For two isolated coils, if we have two coils isolated from each other, there is no connection between them, or one coil is in a place and the other coil is at another place, then the two coils are isolated, then the coupling coefficient K will be equal 0. If we have the two coils tightly coupled, or the two coils are connected across the same leg of the core, as shown in the figure below, we have the two coils connected across or concentrically over the same leg of the core, then the two coils are tightly coupled. If we need to have or we need to obtain a higher value of K, both coils are wound at the same core over each other, as shown in the figure below, as shown here. There are two types of magnetic losses. The first type of losses is eddy current loss. What is an eddy current loss? If a coil circulate a current in the magnetic material, or it is a circulating current in magnetic material, which is a concentric circles, is called the eddy current. EMF will be induced in the path between the time variation, or because of time variation of flux enclosed by the path based on Faraday's law of induction. Consequently, a current will be passing in the core called the eddy current. Both core material has resistance. Then we have power losses I square R, the eddy current square times the resistance, will be caused by the eddy current and will appear as heat in the core. As the material of the core is made of ferromagnetic material, which is also electrical conductive, besides being magnetically inductive or magnetically can pass or can establish flux lines. If we have a flux in the material, then the flux will produce a current. The current will be as concentric circles having the same center and around the axis of the core. What are the main consequences of eddy current? We have two consequences. The first one is the eddy current causes heat energy loss. Due to the resistance and the current, we have a power loss in the form of heat in the core. This heat energy will make the atoms of the material to oscillate, and a collision or collisions happen between the atoms. This collision will increase the resistivity or the reluctance of the material. Then the establishment of the flux lines will be more difficult, and this causes demagnetization of the core or decreasing the flux activity in the core. How to overcome these shortcomings of eddy current? The eddy current can be reduced by two ways. The first way is a higher resistivity core material may be used by the addition of few percentage of silicon to the alloys use of ferromagnetic material or iron, which increase the resistivity of the material significantly. This raises the resistivity of the material and reduces the eddy current. The second method is by laminating the core, or laminated core can be used. Thin laminations are insulated. Also, the thin laminations used are isolated from each other by varnish. This varnish can make the resistance even higher. The laminations are made in the plane of the flux, in the same plane of flux, so as to not affecting the flux activity or decreasing the flux. The eddy current loss can be expressed in the magnetic core can be expressed by the following equation due to time varying flux. PE equals KE, which is a constant, times magnetic flux density maximum square times frequency square times delta square, where delta is depending on the type of material and the lamination thickness. Last term is the V, which is the volume of the material. The lamination thickness varies from 0.5 to 5 mm in electric machines and from 0.01 to 5 millimeters in devices used in electronic circuits operating at high frequencies, where high frequencies produce a higher value of eddy current loss, as shown in this equation, as it is related to square of the frequency. The second type of magnetic losses is the hysteresis losses. As the alternating magnetic flux magnetizes the core, the energy is lost in the core due to the hysteresis effect. What is the hysteresis effect? The energy loss, called the hysteresis loss, is proportional to the area of the hysteresis loop. And the hysteresis loop depends on the ferromagnetic material of the core. Each time the magnetic material is made to traverse or form its hysteresis loop, it produces a power loss. The hysteresis loss stems from the molecular friction, as the molecules of the atoms collide with each other, and a friction happens due to the uh, a change of polarity of the north and south poles due to the change of the current direction, as it is AC. The magnetic domains are forced to reverse their direction by the applied magnetomotive force. We have here the initial curve, which is the dotted part, this dotted part. As we magnetize the material initially, it begins from flux density and H equals 0, and by increasing the H or the I, we get an increase in B, as we have seen in the BH curve, until we reach the maximum value of the magnetic flux or the saturation. In the part that the current decreases, we have the current in the form of AC or sine wave. Then from point O, this is point O, to point A, which is the maximum value of the current, we have this point A. When the current decreases from A to B, then the flux will decrease until we reach the current equals 0, but we have a part of the flux which is called the residual magnetism, or the magnetic flux that remains in the core. Now the current will reverse its direction from B to C, will reach the maximum current in the negative direction. First of all, the residual magnetism will be decreased to 0, then it reverses its direction as current reverses until we reach point C. From C to D, the current decreases, but the material will store a part of its the magnetism as B residual in the same as the positive value but with negative sign. From D to E, this is point E, we have the point at the top, or the maximum positive. We have the flux reverses its direction until it reaches to 0, then it will return back in the positive to point E or point A. Every cycle of the AC supply, the material will traverse this hysteresis loop, which is an energy loss due to the energy stored in the material. If we need to calculate the hysteresis losses, we have P power due to hysteresis losses equals KH, which is a constant whose value depends on the ferromagnetic material. times the flux density maximum power n, where n is excitement's exponent, which is between 1.5 and 2, times the frequency and the volume of the material. There are two types of magnetic materials. We have the hysteresis loop can categorize materials to two types. Materials with higher residual magnetism. These materials will store a higher value of residual magnetism, called better magnetic material or hard magnetic material. They have high hysteresis losses, but it can be used for cases or applications like DC motors or motors, where we need residual magnetism to be present in the poles of the motor. For the second curve, we have lower BH or B residual, where the area under curve is smaller. We have lower B residual. These materials are called soft magnetic materials or worse magnetic materials. We have lower hysteresis losses, which is the area under curve. And for materials needing lower magnetic flux or residual magnetism, this will be convenient or suitable for applications like transformers and induction furnaces or induction machines. Let's see an example. We have a coil with number of turns n equals 500. N equals 500. The mean magnetic path L core equals 360 millimeters, which is the length of this path L core. The air gap lengths, we have two air gaps here, the air gap at the top and the air gap at the bottom, having both the same length, which is 1.5 millimeters. We have flux density of 0.8 Tesla is required to actuate this relay. The material core is cast steel, fringing is neglected. Calculate the current in the coil. The second required is permeability, which is mu, and relative permeability mu r. Last, if the air gap length is equal to 0, the two parts, movable part and fixed part, attracted, then the length of the air gap will be 0. You need to find the current in the coil at the same flux density B equals 0.8 Tesla. Now we have the type of material, which is cast steel, and we have the B. We can enter the BH curve with B 0.8 and reach to the curve of the material, which is cast steel. Then we will move downwards to measure the value of the H. We have H from the curve equals 510 ampere turn per meter. Now we can calculate the magnetomotive force of the core, which is equal to H core times L core. We have H core from the BH curve 510 and the length of core, which is equal to 360 millimeters, or we divide by 10 power or multiply by 10 power negative 3, then it will be equal to 0.36. 510 times the 0.36, we have 184 ampere turns. For the second part, which is the air gap, we have two air gaps. Then we will multiply by 2. H gap times L gap multiplied by 2, where H gap equals B gap divided by mu naught, where B gap 0.8 and mu naught 4 pi times 10 power negative 7. We have the magnetomotive force due to the air gaps equals 1910 ampere turns. Then we add both F or magnetomotive force from the core and the magnetomotive force from the coil. We got the total magnetomotive force 2094. From it we can get the current in the coil. Ni equals N times I equal the magnetomotive force. N times I equals the magnetomotive force, which is equal to the N or I equals F divided by N. We have magnetomotive force and N dividing these two values, we got the current 4.19 ampere. The second required is the permeability of the core. We have B equals mu times H. We have here B and H. We can get mu by dividing B core divided by H core. 0.8 divided by 510. We have mu core equals 1.57 times 10 power negative 3. After that, we need to get the relative permeability. If we divide the permeability of the material by the permeability of free space or the air, we have the value of mu r equals 1250. For the part after that, we need to get the H of the core only, as there will be no air gaps as attraction happens between the movable and fixed parts. Then we have magnetomotive force F equals H core L core. We have H core 510. We have obtained this value from the BH curve, and 0.36, which is the length of the core given in the example, but we have converted it to meters. Then we got F equals 184 ampere turn. From the magnetomotive force, or HL, we can get I equals 184 divided by 500, which is equal to 0.368 amperes. We will now see another example. For a magnetic material having an N turns equal 400, length of core equal 50 centimeters, and length of the air gap 1 millimeters, we have cross-sectional area of the core and the air gap are equal to each other, equal 15 times centimeter square. We multiply it by 10 power negative 4. The relative permeability of the core is mu r equals 3000, and the current I equals 1 ampere. We need to find the flux density in the air gaps, and the inductance of the coil. First, we will calculate the reluctance of each part. Reluctance of the core equals L core divided by mu naught times mu r times area of core. All are given. We now can calculate R core, which is equal to 88.42 times 10 power negative 3, 10 power 3, ampere turns per Weber. For the reluctance of the other part, which is the air gap, given here, we have the length of the air gap. The permeability of the air gap is equal to mu naught. This is a very important note. The permeability of air equal to mu naught, and we have the area of the air gap, which is equal to 15 times 10 power negative 4. From the calculations, we can obtain the value of air gap reluctance, which is equal to 530.515 times 10 power 3 ampere turns per Weber. Now we will add the two reluctances to get our total, R core plus our air gap. We need to get the flux. The flux will be equal to magnetomotive force Ni divided by the total resistance of the circuit. We have 400 turns, and the current equals 10 ampere divided by the addition of the two reluctances. Then we get the flux of the core. The second part, we need to get flux density. Then we divide the area of the core by the the area of the air gap, which is equal to 0.6463 times 10 power negative 4 divided by 15 times 10 power negative 4. Then we got the value of the BH equals 0.4309 Tesla. The second, or the last required, is the inductance of the coil. We can divide n squared by the summation of the reluctances we have got, we have obtained before or earlier in this part, we got L equals 258.52 times 10 to 3 Henry. We can also get the inductance using the self-inductance or N phi over I or lambda, which is the flux linkage. We can get the inductance having the same value as the previous step. The last example in this lecture, we have two identical coils having number of turns equal 500 turns, are wound on the same magnetic core, are connected on same core, the current passing at a rate of 2000 ampere per second, and the coil induces a voltage of 20 volts. This is induced voltage across the second coil. The first required, what is the mutual inductance of the arrangement? We need to get M, which is K root 1 L1 L2. And also, if the self-inductance of coil 1 or coil 2 equals 25 millihenry, what will be the percentage of flux supplied by coil 1 linked to coil 2? This depends upon the configuration and the coupling between the two coils. As the two coils are identical, then the mutual inductance M21 equals M12 equals M, and for the number of turns, which is also equal, N1 equals N2 500 turns, L1 equals L2, we need to get the value of the mutual inductance. Then the I by the T equals 2000 amperes per second, and V2 equals 20 volt, L equals 25 millihenry. We have V2 equals M21, the mutual inductance, times di by dt. We have V2 equals 20 and di by dt equal 2000. Then M will be equal to 0.01 Henry. Now we have to obtain the coupling or the percentage of flux set by coil 1 and links coil 2. We have the mutual inductance equals K times L. The mutual inductance equals 0.01 we have obtained here before equals K times the inductance, which is equaling to the value of the inductance. Then we got the value of K, which will be equal to 0.01 divided by 25, and we obtain K value of 0.7, which is the coupling effect between the two coils. Or this means that 40% only of the flux links the other coil at the other side of the coil. Now we have finished the lecture about magnetic circuits. See you in next lecture.